But good morning, everybody. Welcome to our session here today. As introduced, my name is Evan Bentz at the University of Toronto. I'm a professor in the Department of Civil and Mineral Engineering. And I worked here with Mike Thomas. And so I jumped at the chance to basically talk about Mike for a bit. And you're going to see that this session is more about stories and less about the alkali silica reaction. Why is that? Well, Mike Thomas worked at the University of Toronto from 1994 to 2002, after which he moved to UNB. And I was a grad student in 1994 to 2000, and I've been a faculty member ever since, actually. And we worked together on the computer program Life-365. So we have here a picture of Mike from September 4th, 2001. You can see that he is in Greece at the what's called the Erechtheion, which is at that stage, 2,400 years of service life, basically. What mystifies me about this picture is that when I was there in 2003, you couldn't actually get that close to the Greek structures. Which means Mike either jumped the fence to get there, or before 9/11 you could get up close, which was good. You can also see that I've been watching Law and Order, so I ended my slide there saying these are their stories. Basically, some of the things are going to happen with regard to our overall trip. So first of all, okay, so the next slide basically is what it's showing here is the manual of computer program Life-365, because what Mike spent most of our time working on together. My PhD was actually about structural engineering stuff, but we were working on the program called Life-365 at the time. And I want to briefly explain what that program is. So some of you have used Life-365 and you know what it is, but I'll tell you what it is anyways, just in case. What it is a computer analysis program for estimating service life. And what we see here is the main screen of the original version of the program. So we have here an 8-inch thick slab with some details about it and a certain design life. Surface chloride history that is selected for the location, which was Chicago for this one, with a temperature history as well, and a series of different scenarios was the idea. And the intention of the program was to allow the engineer to compare different possibilities. In this made-up example, for example, we have the difference between a base case with regular black steel and conventional concrete, or calcium nitride, or epoxy-coated steel, or high-performance concrete, or regular concrete with a sealer on it, or indeed what we call the user snake oil in this example, just someone's going to sell you a product that they think is going to do a wonderful job. The idea was to allow one to have a comparison of these different options on an equal playing field. So from that, we can detect which one's better, which one's worse, and which one the engineer should perhaps conclude or select. This was one of the ways that the results were actually summarized. And what this is showing basically is on the horizontal axis is the time horizon in years. The construction time would be over here at 0, and the time the structure would be salvaged would be way up perhaps at 75 years. Vertical axis is cost in dollars per square foot of the different options. And the idea is before the first repair happens, the cost is constant, assuming that the maintenance cost year by year are relatively small. And then there'd be the first repair, second repair, third, fourth, fifth. And the idea was that you could compare these different options we had before and see basically how until the first, at time 0, the cheapest option in this example was the base case, just regular concrete. The most expensive option was actually the snake oil. The other ones were in between. But the base case also required a repair early on, which then had a present value cost of that repair that would increase the value. And then it would go up, the cost would go up higher and higher as time went by, such that by the time we got to 75 years, in present value terms, the base case concrete was the second most expensive. The sealer was actually more expensive. The epoxy made more sense in this example. The calcium nitride corrosion inhibitor also made sense. High performance concrete made the most sense, although the product that was the user design product called the snake oil ended up being the best in the very long term, but it also assumed there'd never be a repair, which may or may not be credible from the perspective of understanding things. And then we could put these together into a summary page that would allow us to basically be included in design calculations saying this is the comparisons we have for the initial cost, the repair cost, the percentage area repaired, et cetera, the different parameters to get the final number for the total life cycle cost. Sorted by basically the cost. The user-defined ones where you could specify all the input parameters were separated to make sure we could see them. And this is basically what the program would do as a useful tool to allow engineers to make these comparisons. Another thing you can see from these comparisons, though, this particular example was actually made by Mike. You can see his initials right there for a Concrete Corrosion Inhibitors Association seminar. And you can see the file was made on the 28th of May, 2001, a little bit early in the morning, suggesting that Mike's clock wasn't right on his computer at the time that he made that file. And so where did that program come from? Some of you have used that program either on the web version or indeed that original version itself. And I want to tell you the story about how it came about, because I think it might be of interest. It started here in 1995 when Mike was teaching his first course. He taught me a first course, actually, the first lecture on October the 6th of 1994 in Doug Hooton's course of concrete construction, where he talked about alkylate aggregate reaction. He did a good job. And the first course that I took with him was, I think the first time he taught it was the repair and maintenance course in January of 95. And it actually led to the development of Life-365 itself. This right here from February 95 is the proposal for the project in that course that ultimately turned into program Life-365, basically. And I was a graduate student at the time. I was suggesting that it be a group effort between me and my friend Chris and my friend Savio. In the end, it was just me and Chris that worked on it together. And you can read all that, but the key thing to note is that the proposal was to develop a computerized finite difference model of concrete 2 dimensions, blah, blah, blah. You can see more discussion. And we said, using these overly complex methods, that was a joke, that involve substantial nonlinear synergistic effects, that was Mike's favorite word at the time, that we can get a good mark on a plethora of pints. That's what the goal was at the time as a graduate student, but I didn't realize that 25 plus years later, I'd still be talking about it. Indeed, some of you might regret that that's the case, but here we are. The redacted section was something that was private information that is we can't release from privacy issues, which is quirky, but there we go. That's February 95. Now, Mike is always interested in showing things well, actually, and we can see here that he set up the first international symposium on repair and maintenance of concrete structures at the end of that course. What this was actually was the presentations of the course projects. But because we had international students, he called it an international symposium, which was great fun. And we have a whole bunch of names here, some of which you'll recognize actually from that first year of classes. And this was the one that ultimately became the version of Life-365 in effect by Bentz and Chris Evans. But I think it was Mike that made the joke rather than us. He renamed the title of our presentation, Possible Applications for Tetris and Concrete Repair. We got the last laugh, though, because this was done in the large lecture hall here at the university. And it had, in 95, which was very unusual, it had a large display screen at the front of the class. And at the end of the class, we actually played Tetris on the big screen, which made him laugh. But then we also showed a game called Descent, which was a 3-dimensional flag shoot-'em-up game, which we told him was a representative of the internal pore structure of concrete. And we speculated at the time about whether someday we would actually have virtual reality flying through concrete pore structure. It hasn't happened yet, but maybe it has. I just don't know about it. But it was quirky. But as usual, the take-home lesson from this is Mike has a good sense of humor, and that's a great thing to have as a professor. The final report for that project was on April 11th, 1995, and you can see what we did. Basically, Mike had data from the building research establishment that he had cast, I think, in the 80s, I guess, and had a series basically of exposed specimens in, I think it was salt water. And he had a series of boreholes, or not boreholes, but drilled holes in to basically look at the amount of chloride that had percolated into the concrete. And one of the things he was worried about at the time was A, how do you deal with the background levels? And B, do we have to worry about this being a 2-dimensional shape rather than a 1-dimensional shape? And it turned out that I had done work previously in my undergraduate degree on how to do finite difference, which is what the project ended up being. And as a result, we were able to make good progress in both of those questions. It ended up dealing with the background was easy. You just start with an initial profile and propagate through. These are some of the results from that report. And you can see that we were curve fitting to this data, of course, so that's why it worked. But it did work quite well. It looked very worthwhile. What was perhaps new at the time was, in fact, the bottom graph down here showing that the 1-dimensional model for this data on top is the blue line. The 2-dimensional model for the same data is the dashed line. You can barely see the dashed line back here because it's almost the same. That is, for the geometry we have up here, most of the flow in this region here, indeed from the all four sides, is actually essentially 1-dimensional. And we'd have to get a lot more flow, indeed a lot more time going by before the 2-dimensionality would matter. And that was a worthwhile thing to learn. But Mike is no fool. He then proceeded to get the following year another student to check the results because it's totally possible that what we said was not true. So Pierre Pung did work on that to find out whether the results were good. And they turned out well. And so we kept on working on it, which was good. He then wrote a paper in Dundee from 1996, actually with me as an author on it, which made me as a master's student feel very special. There was an ACI paper in 1998 on the model with me as an author, a 1999 paper that's primarily about the data, so I wasn't an author on that one, but there was over 1,000 citations between these different papers and indicating that Mike is generous with his ideas. He doesn't want to take all the credit for himself. He wants to share it, which again is a sign of a good engineer and a good professor. Later, there was a version that had an interface in it in 1996, and indeed a version with wicking, capillary suction in it in 1997, which indicated that we kept on working on the program together as I worked on now my PhD, and he continued as a Professor. The big change happened in 1998 when there was a session set up at NIST, at the National Institute of Standards and Technology. They had one of their sessions set up here to try and answer the question, what should we do about modeling of service life? So this is the official report that came out of it in the end. And in that session, there was people, we call them now stakeholders from all across the industry, looking to ask the question, what should we do? And there were already computer programs that some of the concrete suppliers had, and some of the construction material suppliers had as well, that were being used to basically to advertise products. And so there was discussion, should we just use one of those, or should we use something different? And Mike made a strong argument at that session, actually, that we should have something that's independent of any of the suppliers, because if it comes from the suppliers, it might accidentally, or indeed maybe intentionally, be biased in a certain direction. So in the end, this is the summary of the recommendations from that grouping. And what basically it said, briefly, number one said we should have something associated with Committee 365. Number two said we should have a basic model. That was the program Life-365. Number three said we should do more science. Yeah, that's happened too. Number four said NIST should be in charge of the whole thing. That didn't end up quite happening that way. But the overall conclusion was basically that a subcommittee be set up in Committee 365, Service Life Prediction, with the purpose of carrying out the recommendations. And Michael Thomas of the University of Toronto was invited to become chair of the new subcommittee, and he accepted the appointment. And so away we go. Oops. So what are some of the lessons that I learned from the development of Life 365? The first one was that key point about having an industry independent program. As I was coding the program, I intentionally didn't look at all the people who had existing code sent them to me saying, hey, have a look at this, see if it'll help you. I intentionally didn't look at them because I wanted to make sure that it was a clean room development, as it's called, completely independent of any previous work. And then I checked at the end for comparisons. One of the things I found was that one of the tools that the industry had been using suggested that bridge decks would have 4.8% of reinforcement in them. Now in Ontario, they have 1.2% reinforcement in them. And 4.8% is a representative value for a heavily loaded column, for example, and you could use the program on a column, but it was being represented as a slab. Of course, what this meant was if you had anything that changed the cost of your reinforcement, stainless, galvanized, epoxy coated, all those would look extremely expensive compared to the products that that company sold. That made it clear to me, and it turns out the users of the program weren't even aware that the program had made that strange assumption hiding inside it, actually. So having something that's independent of industry to have a program to allow you to compare different options is a good idea, and it's cleanly a good idea, and that was Mike's idea. The next thing I learned from that development was how long did it take to write it? And you'll see beside that the Greek letter pi. What happened was when Mike was asking me to send him basically a proposal to write the program for Life 365 for the project that he was involved with, I added up all the number of hours I thought it would take to write the program. And most of that program was the interface because the actual core of it already existed in that project from the course a few years earlier. I ended up calculating it should take 65 hours. I then asked another colleague, my PhD advisor at the time, Michael Collins, who is my other example of how to be a professor and do it right. And Michael said, you should apply an optimism factor to that. And he recommended pi. So I took the estimate of 65 hours it would take to write it and charged Mike for 200 hours and counted the hours. In the end, it took 208 hours. So I learned from that in fact, pi is my optimism factor, which I think means I'm a rather optimistic person. I know some people whose optimism factor is E, or indeed pi over 2. But I like the idea that pi is got more significant figures, so it sounds more precise. Next question from the development was, what do we call the program? And it was unclear what to give it as its name. And Mike and I discussed various things. And one of the suggestions was, well, Committee 365, I mean, there is 365 days in the year. And so it's not necessarily named after the program, but number of days in a year. And I supported that argument. Mike made the joke that means the program would be misnamed every 4 years during a leap year because there's 366 days during some of those years. But we ended up calling it Life 365. In retrospect, that might have been a mistake. Committee 365 from ACI didn't approve this program. They basically had a subcommittee that was deciding what a program like Life 365 should be like, what its tools should be. And that's still the case, but it has been a little bit confusing. The other lesson from the development was that there's a lot of comments from reviewers. And this was a good thing, of course. This is how computer programs are supposed to be written. And so as a result, having lots of comments showing different perspectives was a worthwhile thing that I learned from that whole thing. This is one of the pages of that right here from March 28th in the year 2000, actually, whereby we're looking at basically what the reviewers' comments were. And this is the copy that Mike gave to me. And what I wrote in my handwriting underneath it was, this is a 2-month time bomb. At this stage, I just started basically being a professor, and it was now March 28th of the first time I was teaching a course, because I started in January 2000. And things were busy. And so I didn't imagine that in 2 months later, when this was going to be due, I could get it done. But you can see the check mark saying, yes, it's a time bomb, but the crossed out meaning, no, it didn't blow up. It was a dud. We were able to respond to all the comments appropriately and get the job done. Now, things kept on going from there. And so the next thing that happened was the fall 2001 conference in Dallas, where Committee 365, which Mike was now the chair of, had a session talking about designing for 100-year service life. And you can see I underlined my title at the bottom to make sure I didn't forget which one was me. And by this stage, we're talking about probabilistic modeling now. And this was saying, let's go beyond what Life-365 does and try and account for some of the variability. And so what that modeling allowed us to do was basically to using a Monte Carlo method that was a simplification from that came from Kyle Stanish, who is now the chair of ACI 365. And indeed, I think Committee 365 is meeting right now. And with that, and with some assumptions on the variability of the input properties to the program, we're able to come up with a histogram basically of the expected lifespan of a particular structure until initiation. This was the key thing here. So in this example, I think it was 6.4 years was the deterministic time to initiation, and the distribution ended up being log normal in effect, with 32,000 individual calculations for the, Monte Carlo spelled wrong. I'm sorry, that says Monte Carlo. And this was very worthwhile. And it also wrote a paper that allowed us to see how we could do those calculations in an efficient way. But the big thing that I learned from that one was probabilistic modeling can be dangerous, in my opinion. The distribution that was on the graph before, the histogram, actually can be modeled just with simpler parameters, and that's what the paper talks about, to give that dashed line. You can see a very grotty dashed line there that came from Excel many years ago, actually. And you can see that the 50 percentile time to first initiation was here. But because we didn't know, and I think we still don't know, basically the kinematics of, or the operations of how initiation works, we simply added 6 years. And so what it meant was that there's a totally deterministic estimate of what the initiation time is as just a constant, meaning that you take the distribution you have from your fancy model and just offset it by 6 years. And this was the potential danger with it. When the result came in before that said the expected time of first repair would be 13 years, 12.9 years, you'd say, okay, plus or minus, yeah. But when you have a probabilistic modeling of part of your analysis, but not the rest of it, now you'd say, well, the probabilistic results are from 9 years out to 20 years. That's very practical. It's very worthwhile, but it didn't include any variation associated with the initiation time. And having a single deterministic number that you know in your head is not the whole story is one thing. Having a range that's not the whole story, I discovered, is much harder to grok, as they say, much harder to understand. To say that there's a range of numbers, but that range is not the whole range is confusing. So from that, I learned to be very careful when using probabilistic modeling, because it can lead one astray very easily, and that can be problematic. As things continued on with Life-365 and versions like it, Mike moved on to the University of New Brunswick in 2002, but we continued working on some things. And one of the things that we spent a little bit of time on, but not much, was comparing Life-365 basically to a spreadsheet. Because it became clear to me after I started teaching finite element analysis here and had doing more work with finite difference that, in fact, we could do it all with a spreadsheet all by itself, actually. I was going to write a paper about that, but decided not to because it turned out that it was too complex. And that having it as complex as that didn't actually help. And so Life-365 continues to be a computer program that you can use online from the web, and it works quite well. What's happened since then? Well, since then, as I've been teaching the finite element course, I decided to make the writing of Life-365 into an assignment in my finite element class. So this is due the February 5th of 2021. And I teach the students how to do this, basically. And so while 25 years ago, I wrote Life-365 as a project and then as a computer program, now every student who takes my finite element course has to write their own version of the program, in effect, but with no interface. Using MATLAB, it's usually pretty easy to do, actually. And so 250 people have now written their own version of Life-365 since that time, actually. And I asked them, of course, to compare to the theoretical solution of the error function for the simple case they look at. And that does the job quite well. So in conclusion, what do I learn from this whole process of working with Mike Thomas? This is a picture from the University of Toronto in 2002, basically just before Mike went to UNB. And that was that there's a part of what we needed to learn about the service life modeling part was the technical part. The rest was how it all fit together with how people and engineers' minds actually work and how we actually see things. And in the end, Mike was the best person to guide me through that whole process, actually. I read an introduction to a paper that was written by Richard Dawkins one time, and he said that there was a person that he knew who you had to have at conferences. And if you wanted to find him, he'd be in the bar at the conference, and you should go and talk to him because the person was always worth talking to. And in fact, if you're scheduling a conference and that person can't be there, you reschedule the conference to make sure they can. And I think he was talking about Mike Thomas. And so was I. Thank you very much. I wish there was a way to hear people so I could know whether anyone was even smiling during that, but I couldn't tell.
Oh, I think there was a few smiles in there.
That's good.
Okay, thank you, Evan. It was a very interesting talk, and it was actually very informative for me. I never really knew the history of 365. So we do have a couple questions, and I think we have time for that. So first one was, regarding organic corrosion inhibitors. Wasn't that part of the study originally? And if it was, what is the effect on the life specified in the 365 service life model?
Well, from that side of things, in terms of what the behavior was more Mike's concern. My concern at the time was basically making sure the computer worked properly. And so they would actually, using various products to your concrete, would actually change the properties of the inputs to my model. And I hesitate to answer that because I think there's 151 people who know that answer better than I do, specifically Mike Thomas, actually. So I don't actually fully know the answer to that one.
Well, that kind of leads to the second question. And the person asked, do you believe that the program can one day take into account the change of fineness of the constituents, such as different blanes for different cement types or SEM particle size?
Well, those sorts of things come into the fundamental parameter, which is the bulk diffusion constant, which is sort of the core value that we're using in our calculation. And that number that the program recommends is a coarse estimate. It's based on water cement and fly ash and other constituents as well, and of course age. There's a lot more variables than that. And so things like the blane number and like almost certainly are important, but we don't have those as parameters actually as inputs, because usually as a designer, you'd say, well, I don't know what those numbers should be. And so what is the designer supposed to do in that case?